Hello everyone, welcome back. In a previous video, we understood what is red-black tree and then understood the properties of red-black tree and the difference between avial tree and red-black tree. In this video, we will cover the different self-balancing techniques used by red-black tree during insertion process to keep itself balanced, so that the worst case time complexity for a tree operations like search, insert, or delete stays within log of n. So before watching this video, if you cover these two videos, then it will give you the base knowledge to understand the things mentioned in this video in a better way. So let's start. In a previous video, we understood these red-black tree properties. These properties are used by red-black tree to keep itself balanced. Now we might get a question how these properties actually help red-black tree to stay balanced. So out of these 5 properties, we need to understand these 2 properties closely. These 2 properties actually help to stay the tree in a balanced shape. How? Let's try to understand with the example. Let's say we insert 60. So the new node color is always red in a red-black tree. But now the 60 is a root. So root, we need to change it to black because root is always black in a red-black tree. Now let's say we insert 70. Red-black tree is a binary search tree. So 70 is greater than 60. So it will be added to the right side based on the binary search tree properties. So 70 is added as a right child of 60. There is no violation here. No properties of the red-black tree are getting violated. Now let's say we insert 80. Now 80 new node inserted, new node color is always red. So here if you see, it is violating this property where no two red nodes can be connected directly to each other as a parent child. So this is not allowed, right? So this property actually helps to avoid tree growing because of just red nodes, right? So it is helping to avoid that skewed structure. This is already a skewed structure, right? Now we might think that why not recolor one of them? Maybe recolor 70 to black or recolor 80 to black. Let's say we recolor 80 to black. Now, okay, this property is fine now, but the tree structure is still skewed. Now this property helps to avoid this skewed structure. So this property, we know that every path from node to its descendant null nodes must contain same number of black nodes, which is also called as a black height. And it is true for every node. So for every node, let's say for node 60. So descendant null nodes. So this is one path, null is left is null. So 1 and left is null. So null is also considered as black. So let's say if we consider that also, so 1, 2, and here it is 1, 2, and if I take null also in consider null also, then 3. So it is not matching, right? For every path from 60 to its descendant null nodes, the number of black nodes are not same. The black height is not same. Here it is 2, here it is 3. So it is violating this property. So this property actually helping to avoid the skewed structure because of this alternate red-black node, right? So we saw that these two properties actually helping to avoid this skewed structure and make the red-black tree balanced, right? But now we need to insert the new node, right? So what is the different way to insert the new node and avoid this skewed structure, right? So in such cases, when we still need to insert the data to tree, the red-black tree self-balancing techniques comes into the picture. So let's say we face the issue which we saw in a previous slide. We still need to insert the node 80, right? So red-black tree uses recoloring first. So recoloring means that it changes the color of some nodes based on some rules. So basically from red to black or black to red without moving them. So it tries to basically perform the recoloring as a technique first. So it is the quick fix to avoid the tree structure changes because that is more expensive. But recoloring is done only based on certain rules. Now let's say if recoloring doesn't help, then the red black tree uses rotations. So the rotation means rearranging the tree a little bit, just between three nodes. We'll understand what this three nodes is in our next slide. But consider it as a smallest impacted subtree, right? To fix the imbalance. Now these three nodes, depending on the imbalance structure of these three nodes, the specific rotations are applied. So depending on the structure of this three nodes imbalance, uh, we can apply specific rotation out of this four rotations. It is similar to A-wheel tree and these rotations are explained in a detail in that video. So red black tree also uses the same rotations. So first it tries recoloring. If it doesn't help, then it goes for the rotations. Now let's understand how those techniques are used, right? So let's say in an insertion process, let's come back to our problem where we still want to insert the new node to the tree and don't want tree to become skewed, right? Or unbalanced. So let's understand. So what rule or property of the red-black tree might break while adding a new node? What is the first property of the red-black tree gets violated during insertion? It is no two red nodes can be next to each other, parent and child. Now, one question might come to the mind that why? Why only this property gets violated first? Because we know that new node in a red-black tree is always added as a red color. So it might cause a red-red violation. Right? Parent might be red and new node is always added as a red. So it will definitely cause the red-red violation first. Right? So this red-red violation helps us to detect whether it is disturbing the balance of red-black tree or not. And using this red-red violation conditions, it tries to fix the imbalance. Let's understand. So the first technique which we discussed, recoloring. So in the insertion, let's understand how recoloring comes into the picture and in what cases. So let's say first step, let's understand the logic or algorithm of cell balancing in a red-black tree. So new node is always red. So let's say we added a new node 70, but now 70 is the root of the tree. So root is always black. So we converted it to the black. Fine. Now let's say we added one more node 65. 65 is less than 70. So according to the binary search tree property, it will get added to the left side. So 65 new node is always red. So step 2, if the node is not root, then we go to the step 2. What is the parent of node? Basically, the parent of 65 is 70. We need to check the color of the parent. If the parent is black, then we are good because there is no red-red violation. We are not changing the black height because we are adding the red node here. So black height is not changing. So good. But let's say we added 80 also here like that. So it is also added properly without no issue. Now let's say we add 60. Now new node is 60 is red. We'll go to the step 2. What is the parent of 60? It is 65. But parent is red now. So the first property which breaks in a red-black tree is a red-red violation during insertion, right? So it basically tells that there is a violation. Now we need to do some fix. It is not allowed in a red-black tree. So then we go to the step 3. Now fix based on the uncle's color. So this is interesting. Why uncle's color and who is uncle here? So let's say 60 is a new node. Let's say X. P is a parent of X. G is a grandparent of X, right? Parent of parent. And we know that uncle is basically the another child of grandparent. So 80 is the uncle of X here, right? Now, here the uncle of node 60 is 80. What is the color of uncle? It is red. So if the uncle's color is red, then the recoloring fix works. We don't need to do any rotation. Let's understand why. So in our case one, when the uncle is red, what do we do basically? We recolor the parent and uncle to black and make the grandparent red. But it is a root, so it gets again converted to the black. So it is, let's keep it black. And then we continue checking this. We'll come to this third step also in some time. But why, when the uncle is red, then only recoloring helps? If you observe one thing, what do we need to fix? We need to fix the red violation. So if we change the parent to black, then that red violation will be fixed, right? 65 will become black. So black and red is allowed. But now if I change just the parent, then the black height for this 70 will get disturbed. How? Let's say black height for 70, here it is 1, 2, and let's say some null node, it is 3. And on the right side, if the 80 is red, then it is just 1 and null node also black, so 2. So 2 and here it is 3. So if we just change the parent black, then it will cause the problem to the second property, which is black height of the tree, black height for this node 70. That's why we make the uncle also black, because if you see all the path from node 70 to all its descendant nulls, they are going from these two nodes, right? So if we make both of them black, then the black height stays same for all paths at node 70, right? Because all paths are going from here only. So the count stays same. It gets incremented by 1, but gets incremented by 1 for all paths, right? Now, then basically, why do we make the grandparent red? That is the question. Now, if we don't make grandparent red, then let's say this is not a root. Let's say root is something here, let's say 80. Then the black height for 80 will get disturbed, right? Let's say previously the black height for 80 was 1 only, and right side also some black node 1 1. Now, if we make this black here, then the black height for 80, let's say 80, 70, 65, this part, it will be 2 plus null node 3, right? Here also it will be 3, but another path for 80, right side, it will be violated, right? Here we are basically incrementing the black node count, right? So if we make the grandparent also red, then it will not cause the black height problem on the upstream, right? We'll understand that part also, but I hope that that is clear. So that is why grandparent also we need to make red, but here it is root, so there is no other node on top which might get impacted, right? So this is fine. Now, that is why when the uncle is red, it is safe to make parent and uncle black, so that the black height here for node 70 doesn't get impacted, and grandparent to red, so that the black height for upper nodes which are parent to 70 is also not impacted, because here we incremented, but here we decremented. So all paths still have the black height same. So that's why we don't need to worry about whole tree. So now, so in case of uncle is red, the recoloring helps and we can insert the new node and the tree is balanced only, right? Now let's understand about this case one in more detail. Let's say this is our tree. Now let's say we want to insert 5 here. So which will get added as a left child of 10. Now the uncle of 5 is 25, right? This is P is parent, 20 is grandparent of 5, and 25 is the uncle of X. So red violation is there. Now uncle is red for node 5. So we'll apply the case 1 steps. Recolor 10 and 25 to black. And then make the 20 red, right? Because if we don't do that, let's say for node 50, what is the black height? It is basically 1 for this path, 1, 2, and let's say any null path 3. For this path 1, 2, null 3, 1, 2, 3, 1, 2, 3. So the black height for node 50 is 3, right? If we consider the null nodes also. Now, if we change the black here, now here it is 1, 2, 3, null node also 4. But here it is 3. So it is violating the black height property. That's why we make the grandparent as red, right? So now we make this red. Good, we fix this part here. But now what is the problem? So problem comes here. So in case of recoloring fix, if we fix the recoloring at this impacted 3 nodes, which is grandparent, parent, and X, then the recoloring problem might bubble up. And we need to fix that till root. We might need to fix that till root. Now it bubble up here. So now what do we need to do? So the step 3 in the case 1. Now the X, basically the grandparent now becomes X. And the 30 is the parent of 20. So it is P, and G is the grandparent of 20. And the uncle of 20 is this 70, right? So again, the uncle for 20 is 70. So we'll apply this same rules here. So what is the rule? Make 30 and 70 black. So 30 and 70 will make black. So the black height will not get impacted. So it will be incremented by 1 because all paths from 50 are coming through these 2 nodes, right? So black height, if you see 1, 2, 3, null also if you consider 4, 1, 2, 3, then right null child null is considered as black, so 4. So it is good. Here also 1, 2, 3, null 4. Here also 1, 2, 3, 4. So the black height property of the node 50 stays basically it is satisfied only because we made both parent and uncle as black. And then we make grandparent as red, but because 50 is a root, so we need to keep root as a black, so we convert it to black again. Now everything is fixed, so all the properties of red black tree are fixed, and we basically inserted 5 with just recoloring. We didn't do any rotation. So this is how the red black tree basically have better performance than AVL tree because it's just recoloring the nodes, right? It is not changing the structure of the tree, which is done in AVL tree because it follows the strict balancing, right? So now we understood how the recoloring helps, but if you fix the recoloring here, it might basically bubble up to the upper layer, and red violation can come to the upper layer, and the same rules we need to check and fix at the upper layer till root, right? So this third step, basically this was X, then the grandparent becomes X. So you need to change the X then points here, and we fix for these 3 nodes, and then X will point here like that, right? Now let's take the another case where recoloring might not fix, right? So for example, let's say this is our tree 60, 50, and let's say we add 40 here. Now we can't recolor 50 also because then it will break the black height property. We can't recolor 40 also. So if you see this property, it is violating red violation, right? Now let's see if I represent null node also. So the nulls nodes are considered as a black node in the red black tree. So for node 40, so X is a new node, right? So 40 is a new node. 50 is a parent of that new node, which is P, and 60 is a grandparent. Then what is the uncle of node X? It is this one. So the uncle of new node is null. So if the uncle of new node is either null or black, then we need to do the rotation because in that case, recoloring won't help, right? Here we can't change parent here as a black. Uncle is already black. So if we change the parent to black, then it will basically break the black height for this path, right? Because it is already, uncle is already black here, right? So, and if we increment the black on this side, then it will break the black height property for this node 60. So that's why rotation and recoloring is required if for the new node uncle is black or null. So we need to check the imbalance type. So when we discussed the rotation cell balancing technique in our previous slides, so these are the three nodes which are impacted. So this is the smallest impacted subtree. So these are the three nodes: grandparent, parent, and X. And depending on the structure of these three nodes, imbalance type, we need to decide what rotation we need to apply, right? And the different structure of these three nodes. So there are four structure of these three nodes. We'll understand each structure and what rotation we can apply to fix this. Basically, to rotate this and fix this basically imbalance and red-black tree property violation. So the first thing, let's say here, let's say if we have the tree structure like this, right? So the parent P is a left child of grandparent and X is also left child of parent P. So it is a left imbalance, right? So the structure of these three nodes is left, right? So we know that in a left imbalance, we fix it using right rotation because you need to basically rotate the tree on the right side so that it balances it. And these rotations we learned in a avian tree video also, right? So for a left imbalance, it basically right rotation helps to solve that imbalance, right? Because the tree is growing on the left side, so we need to rotate it on a right side to balance it. So what is the right rotation? Basically the left child of grandparent, because it is a left heavy or left imbalance. So the left child of grandparent becomes new root and grandparent becomes the right child of new root, right? And if the new root had any previous right subtree, then it becomes the left subtree of G, because now the right child of 50 will be 60, right? Like this. Right child of 50 is now 60. So if 50 had any previous right child, then it has to basically come onto the right side of 50, but it was on the left side of 60, right? So that's why it will become the left child of 60, because left child of 60 was 50 before. Now that is empty. So we can assign the right child of 50 to the left child of 60. So that is the third point. So you can see now it actually balanced the structure, but still the red violation is still there. So after the rotation, we need to do recoloring. What recoloring we need to do? Basically, we need to swap the color of new parent and old parent. So new parent we make black and old parent we make red. So why did we do this? It actually solved the red violation. And whatever the black height was there, so whatever the black height was there upstream, it will also get solved because all the paths will come through 50 only, right? And previously black height was basically all paths were coming from 60, right? So now all paths are coming through 50 because we rotated it from upstream. So we need to make 50 black so that the black height we can basically keep proper. So the rotation actually helps the red node to come up, and the swapping of the color between new parent and old parent fix the red violation, which was this, and also the black height of the tree. Because previously, if you see here, if you don't do this, then what are the path which is coming from above? The black height is one on this path, and it is not basically, it is one more on this path, and it is not here because there is no black node here. Here, any path coming through 60 was having this black node counted 60. So that's why we need to make 50 as a black node so that any path coming from above will have this black node still counted, right? And 60 we make red because otherwise it will cause the black height imbalance again, right? So that's why rotation helps to basically bring the red node up so that so that it fixes the red violation and black height of the tree. Now the next structure is this one, where parent P is the right child of grandparent and X is the right child of parent P. So it is right imbalance, which is fixed by left rotation because it is right side imbalance. So we need to basically do the rotation on the left side so that it will become balanced. So the left rotation is basically the right child of grandparent becomes the new root and 80 becomes the new root and the grandparent, which is 70, becomes the left child of new root 80. And if 80 had any previous left subtree, let's say here, if we have, let's say here 75, then it becomes the right subtree of the old parent. Because let's say if we have 75 here, now if 80 moves here, where 75 will go? 75 needs to be on the left side. But 75 is greater than 70. So it has to be on the right side of 70. That's why it becomes the right subtree of 70 or old parent. So this is how we fix the red-black tree right imbalance. And then we do the color swap for old parent and new parent. So that the red violation is broken and red height of the tree is still, black height of the tree is still maintained as explained in the previous slide. The next structure is basically left right for this three node. So this is the structure where we need a rotation. So basically P is a left child of grandparent and X is a right child of parent P. So it is a left right imbalance. So it requires the two rotations. One is left rotation at P and then right rotation at G. Why? Because we need to break this zigzag structure. If we don't break this zigzag structure, we will not be able to solve the imbalance problem, right? We can understand, if you want to understand that in more detail, you can check the AVL tree video, but basically first we need to break this zigzag. So we do the left rotation on 50 so that the 60 comes here and the binary search tree property will be satisfied like this. Now, if you see this is nothing but the left imbalance and we know that it is solved using right rotation. So right rotation at G. So if we do the right rotation, the tree will become like this. It helped to bring the red node above, but now we need to fix the black height, which got violated because of this. So how we do that? As mentioned in previous slide also, we swap the color of old node and old parent and new parent, right? So that red violation is gone and the black height of the tree is also maintained. And the last structure is basically right left. So P is the right child of grandparent and X is the left child of parent P. So it is right left violation or imbalance. So we need to do right rotation at P so that the zigzag structure is broken like this. So 70, 80, 90. 80 basically comes here and 90 goes on the right side. So it basically helps to maintain the binary search tree property also and breaks the zigzag structure. So now if we see, this is a right imbalance. So which rotation helps? Basically right side it is imbalance. So we need to do the rotation on left side to make it balance. So the left rotation on G will basically make the tree like this, which is balanced. So now we swap the color of new parent and old parent so that the black height is not violated and the red violation is also fixed. So this is how the right left imbalance is handled in the red black tree. So basically the rotations related to these three impacted nodes, grandparent, parent and X, depends on the structure of these three nodes. So there are four imbalance structure for these three nodes, similar to AVL tree, and we apply the specific rotations based on those three node structure to solve the imbalance and also basically solve the red black tree property violation, which is red violation and black height violation. Now let's take one example. Let's say we want to insert 50, 30, 70, 20, and 10 in a red black tree. So initially 50 is inserted as a root, so we'll mark it as a black. Then 30 is added as a left child of 50. It is fine. It is not violating any property. 70 is added as a right child of 50. So that is also fine. No violation, no red violation, no black height violation. Now 20 is added as a left child of 30. So here if you see it is a red violation. So here what will be the case? Basically, let's say it is X is 20, which is new node. This is parent of that new node and this is grandparent. And this is the uncle of new node. So the uncle of X is also red. So the case one will get applied here. We will recolor the parent and uncle to black so that the black height of whole tree is not disturbed because all paths are going from here, and grandparent we make red so that the whole tree black height property is still satisfied. That's why we make grandparent also red because we are incrementing black here. So we need to decrement by making this red. Now, because 50 is a root, so it will still be black. Even if we make it red, we need to make it black because it is root. So which is fine. So now the tree is balanced and satisfying red-black tree properties. Now let's say we insert 10 now. So again, we got red violation because that is the first property gets violated in a insertion. So now if you see, what is the uncle of new node? The uncle of new node, which is basically the child of 30, it is null. So if the uncle is null or black, then we need to do the rotation because just recoloring this 20 to black will not help because it will basically violate the black height property for 50. It will be like 1, 2, and if we make this also black, then it will be 3 and null as a 4. Null is considered as black, and here it is 1, 2 and null 3. 4 and 3 not matching, so it will violate. That's why we need to do basically rotation and then recoloring on top of that. Now this is left imbalance. So basically we'll fix it using right rotation. So 30 will become the right child of new parent. The left child of 30 becomes the new parent. And the 10 is still the left child of the new parent. So it is good. And we swap the color of new parent and old parent. So that, because if you don't do that, here if you see 1, 2, 3, here it is for this path it is 1, 2, 3, fine. But here it is 1 and just 2. So we need to handle this. That's why we need to swap this color 20 so that it is 1, 2. For this path also it will become 3, null 3. And here also 1, 2, 3. That's why we need to swap the color for old parent and new parent. And this is how all these values are inserted by keeping the tree balanced by satisfying all the red-black tree properties. So we saw how the red-black tree properties smartly helps to make itself balanced, make that red-black tree balanced, right? Without making it skewed binary search tree. So that is the smart logic or algorithm behind the red-black tree cell balancing. So in this video, we understood what are the different cell balancing techniques in a red-black tree and how they behave during insertion use case. When can we apply recoloring and when we need to do rotation? And after rotation, why do we need to do recoloring? And how do we need to do the recoloring and rotation so that it still satisfies the red property and black height property of the tree. In the next video, we will understand the same self-balancing techniques for a deletion scenario. Hope you understood the video. If you liked the video, please share and subscribe. Thank you so much.